Hi guys, this video is on binary tree height bounds. What we're going to work out is basically the minimum and maximum possible height of a binary tree. That actually is an important fact in analyzing binary search trees. So soon we'll see that the binary search tree data structure's efficiency is closely related to the height of the trees. So there's an important question: what is the height of these trees? Let's define n to be the number of nodes in the tree. This is conventional. N is the number of elements in a data structure. And we're going to define the variable h to be the height, h for height. So the question we're going to answer in this video is, what is the maximum possible height of a binary tree as a function of n? And also, what is the minimum possible height of a binary tree as a function of n? So we want a relationship between n, the number of nodes in the tree, and h, the height of the tree. And we want the minimum and maximum of what's possible. So the maximum height is big O of n. This one is the more straightforward of the two. So let's imagine if we stretch out a tree vertically. So just imagine we've got a bunch of nodes and I kind of stretch it out vertically to try to make it as tall as possible. So what happens? You end up with a tall and narrow tree. You know that if you've got a bunch of nodes and I stretch them out vertically, then they're going to kind of pull together and become narrower. And the narrowest possible tree is one where every parent has only one child. So that could be that we have the parent and then we have all left children. It's just following left children all the way down. Or it could be if you start from the root, it's all right children going all the way down. Or it could be a mix, a left and then a right and then a left and a right, some kind of zigzag thing. Here's what those would look like. So on the left, I've got a binary tree where the only child pointers we are using are left child pointers, and this is kind of this left-leaning diagonal kind of thing. And in the middle, I've got more of a zigzag. This one's alternating between left and right. On the right hand, I've got a binary tree that only uses right child pointers. But in all of these examples, this property holds that every single parent node has only one child, and then there's just one leaf that has 0 children at the bottom. The height of a tree like this is the number n minus 1, and that's because the heights count from 0. They start from 0. So all of these examples have 5 nodes, and the height of the root node is 4, 5 minus 1, because we start heights from 0. It's one of these off by 1 things when you count from 0. And the height of the whole tree is the height of the root. So all of these trees have height 4. So the maximum height is exactly n minus 1, and in asymptotic notation, we call that big O of n. So the maximum possible height you can get is linear, big O of n. Now let's get into the minimum height. This one is a little trickier. So now we're going to imagine kind of the alternative reshaping of a tree. Imagine that we kind of smush together the tree vertically. We compress it downwards. Well, what's going to happen? It's like if you ever squeeze on like a peanut butter and jelly sandwich or an Oreo cookie, everything shoots out the sides, right? So what's going to happen is we're going to end up with a short but very wide tree. So what's the widest possible binary tree you can get? That's one where every parent node has 2 children, kind of the opposite of the previous example. So what we're going to do now is draw trees like this, where every single node, if it's a parent and has children, it has the full 2 children. The only nodes that don't have 2 children are the leaves that have 0 children. So we're going to draw examples of that, bigger and bigger trees, and observe the relationship between n, the number of nodes, and h, the height of the tree that we get. So to begin with, here's a tree with 1 node, n is 1, and height is 0. Heights start off at 0, just like depths. And now what I'm going to do is make this a bigger tree. So if I'm following this rule that every node that is a parent has 2 children, then I'm forced to draw 2 children of the root, and we get this kind of a tree. So I have a root at height 1, 2 leaves at height 0. I've got 3 nodes, and height is 1. Let's try to make this deeper. Now, if I add 1 node here, and I'm following the rule that every parent has 2 children, I'm forced to add a second node. So I have to add 2 nodes below each of the current leaves, and we get a binary tree like that. So now we have a total of 7 nodes, 1, 2, 3, 4, 5, 6, 7. N is 7, and the height is incremented up to 2. Let's do one more round of this. So if I add any children to these leaves here, I have to add pairs of children to all of the leaves. And so we add another 8 nodes at the bottom, 1, 2, 3, 4, 5, 6, 7, 8, for a total of 15 nodes to make a binary tree of height 3. Now, what you can notice is the pattern here is that every time I increase the number of levels, I have to add twice as many nodes as the previous time. So to begin with, there's 1 node. Now I have to add 2 nodes. Now I have to add 4 nodes. Now I have to add 8 nodes. This is following the powers of 2, doubling. We've seen these powers of 2 come up also in the way that vectors resize. It had that same 1, 2, 4, 8, 16, 32 powers of 2 sequence. So the pattern here, if we summarize this pattern, is that n, the number of nodes, is exactly 2 to the height plus 1 power minus 1. The plus 1 and the minus 1 there, they're kind of details, but that's necessary to make this math come out perfectly. So, for example, in the third row here, 2 to the h plus 1, so height is 2, so that would be 2 to the 2 plus 1, that's 2 to the third power, which is 8. 8 minus 1 makes 7, and that's exactly the number of nodes n. And this pattern works for all of the rows in the table. So now let's solve that equation for h. We've got this equation that says in a widest possible, shortest possible binary tree, what's the relationship between n and h? Now I want to solve for h because that's what we really want to know. What is the height? So now we're going to do some algebra to solve for this. I can add 1 to both sides, and I have n plus 1 is 2 to the h plus 1. Now what I'm going to do is take the base 2 logarithm of both sides. I've got h in the exponent here, and I want to get it out of the exponent. So if we take the base 2 logarithm of both sides, I've got the logarithm of n plus 1 on the left is equal to the logarithm of 2 to the h plus 1 on the right. There's a log rule here that says when you take the log base 2 of 2 to the something, that's just the something. The log base 2 and the 2 to the power cancel each other out. So we have log base 2 n plus 1 on the left and h plus 1 on the right. Finally, I just subtract 1 from both sides, and the height is equal to the log base 2 of n plus 1 minus 1. So that's approximately log base 2 of n. The plus 1 and the minus 1 do change the numbers here, but we're going to put this in a big O asymptotic efficiency class, and those plus 1 minus 1s are not significant. So h is basically equal to the logarithm in base 2 of n. In computer science, we have a lot of powers of 2, so we have a lot of logarithms with base of 2. So when we write just log with no explicit base, that's assumed to be defined as the log base 2. So we can write that h is big O of log n. That really means the base 2 logarithm of n. So here is the bounds that we found. If n is the number of nodes and h is the height of the tree, then the maximum possible height of a binary tree is h is big O of n. So you can have up to linear height. The minimum possible height of the widest, shortest possible binary tree is big O of log n. So the height of any binary tree is going to be somewhere in between those. It'll be at least log n and at most big O of n. Soon what we'll see is where this log n time efficiency comes from. You might remember the big 5 list of big O asymptotic efficiency classes had this mysterious log n entry, and so far we haven't used it. Well, this is where it comes up, is in the height of well-balanced binary search trees.